So remember, we have the test Thursday, right? And I have basically I just gave you credit for the page which was missing. Remember? So that page I left out, the page with the hardest problems. You just got credit for that. I would say it's my mistake. I again blame the humidity in BibGraves for putting the pages together when I copied it. But do study that, please, because that will come back for the test most likely. All right. Any questions? All right. So I will continue talking about the material that's past test 3 then. And so we're talking about logs. Oh, trash. She's in her office. Mrs. Parker's got, like, what's going on? See here. Thanks, guys. Logs and exponentials. And so I have introduced the logarithm and the exponential already, right? So exponential function with base a greater than 0, a is not equal to 1, is something like f of x equals to a to the power x, right? And you remember, just to give a quick recap, special case, e equal to the limit as n goes to infinity of 1 plus 1 over n to the n is approximately equal to 2.71 and so forth. This defines f of x equals to e to the x, sometimes called the exponential function. So if I'm talking about an exponential function and I don't really specify the base, I'm probably talking about that one. All right, so this e to the x is a very important function. It comes up in all kinds of natural sciences and so forth. And then the other thing we introduced was the inverse functions to these, right? So the graph either looks like this. This is y equals a to the x, a greater than 1. Or it looks like this. This is y equals a to the x, a less than 1, and between 0 and 1, right? And so both of those pass the horizontal line test, right? And consequently, they're 1-to-1, which means that we can invert them. And the inverse function, I'll graph in red. The inverse function is what's called the logarithm. So the inverse function for this one would look something like this, right? It goes to the point, well, both of them go through the point 1, 0. But this one over here, it does something more like this. So here is y equals to log base a of x. In the case 0 less than a less than 1 over here, we're looking at y is equal to log base a of x for a base which is larger than 1. Now, if I drew my graph correctly, the red should be the reflection of the black graph across the line y equals x. These are inverse functions, right? And even though the picture looks different for base less than 1 versus base greater than 1 for the logarithm, they actually have the same range, right? They have the same range. The difference is that for base 1, as you approach 0 from the right, it's going to minus infinity here, right? Whereas if the base is between 0 and 1, as you approach 0 from the right, you're going to plus infinity. I told the other section that that's really weird. Like this logarithm over here, to me, is very strange. I don't remember ever seeing that in an application anywhere. Like the only place I've ever seen that is a pre-calculus class or calculus class. So I don't think it's the case that people typically work with bases between 0 and 1. More often, we like to work with a base which is larger than 1. It's just more intuitive and natural. Speaking of natural, in the case of the exponential function, the inverse to the exponential function is denoted ln. So definition, log base e of x is denoted ln of x, which is short for natural log of x. The key identities for the logarithm as they relate to the exponential are what? We have a to the log base a of y is equal to y again, and log base a of a to the x is equal to x again. This is for y positive, and this is for any x. All right? And so those are like key identities for the logarithm and for the exponential. This, in some sense, shows you how you can undo the logarithm or undo the exponential by taking the opposite function, right? So let me actually, so I showed you some calculations in the previous time we talked about this using like a box and filling in the box. There's another way we could think about it, which is just like by direct application of these identities. And maybe that's a better way to think about it. I don't know. But just to show you an example of this sort of thinking, if I wanted to calculate log base 2 of 16, then what I could do is, since 16 is what? What is 16? 2 to the what? 2 to the 4, right? So then this is just equal to 4. So that's kind of nice. It's a direct calculation. Of course, this is not always possible for a given value, right? Like not everything happens to be, a value raised to that power, but I'll do another one here. What if we had like log base 10 of 1 over a million? How could we could calculate that? We wouldn't even need a calculator. That's log base 10 of what? 10 to the what? A million is 10 to what? 1 over a million, rather, is 10 to what power? 10 to the 6th would be a million, but this is over a million, right? So it's 10 to the, minus 6. And so you're fine. I think I asked what a million was, and I was looking at the board, but I was saying a different thing, so you're fine. So what is this is equal to? Minus 6, right? All right. So this only gets us so far, right? The other thing we need to know about are laws of logarithms, right? I can't remember if I told you guys laws of logarithms yet. I don't think I have. Even if I have, it's good to do it again. I don't think I have, though. Law of logs. Say logs. And so the log base a of x times y is log base a of x plus log base a of y. Of course, you could equally well say these things for ln, right? ln of xy is ln x plus ln y. That's what that looks like in that notation. There's also a power property, like log base a of x to the power p is equal to p times log base a of x. That's another thing that's true. And then you could look at like a quotient, right? Like log of x over y. How would that work? Let's think about that. That would be log base a of x times y to the minus 1 power, right? So if we use this one, we get log base a of x plus log base a of y to the minus 1, right? But then we can use the power property to pull minus 1 out, right? So this becomes log base a of x minus log base a of y. So let me just record that for future reference. Log base a of x over y is equal to log base a of x minus log base a of y. So these three properties are critical to working with logarithms. Now, so can you tell me what is our assumption as I write these equations? What's our assumption about x and y? What's the fine print, so to speak, here on that equation? What are we assuming about x and y? What do we need x and y to satisfy in order for log of x to make sense and log of y to make sense? Mm-hmm. What's the domain of the logarithm for any value? What's that? Nope. No, the domain of the logarithm is the range of the exponential. Yep. So in other words, I must know, in order to apply these properties, that x and y are positive. Like the log of 0, that we cannot calculate. That does not defined. Log of a negative number also not defined for us. All right? As with most things, and if you study complex analysis, the log of a negative number has meaning. But that's not this course. So in our context, we can't calculate the log of a negative number, right? So these are critical, right? Now with these, we could do things like, we could simplify logarithms, right? Like, let's look at an example. But while I'm erasing though, let me ask you a question. F of x equals to the log base 10 of 3x minus 7. What's the domain of f? Find the domain of that function. Nope. But the thing is, we're evaluating the log at 3x minus 7, right? Now, if it was just x, you'd be right. It'd just be all positive numbers, right? But you have to think about what we need. We need 3x minus 7 greater than 0, right? So whatever that works out to, that would be 3x greater than 7, so x greater than 7/3, right? So the domain of f of x here would be like 7/3 to infinity. Let me give you another example. If we wanted to find the domain of f of x for f of x equal to the log base 3 of 16 minus x squared.
So it'd be 4. X 4 to infinity, right? You'd have to solve for it, right?
Well, 4 is involved, I think, but let's think about it. We need 16 minus x squared to be greater than 0, right? So how do we solve that kind of inequality?
Minus 16 on both sides.
Oh, you want to move it to the other side? So that's x squared minus 16 less than 0? Or is that?
No, that's what I said, negative x squared. Yeah, negative x squared. Yeah. You not do that?
Well, I mean, I would suggest x squared minus 16 is less than 0. I mean, multiply this by minus 1. Well, I suppose you could say that this is 16 is greater than x squared.
Square both sides.
Square both sides.
Yeah. Or square root, my bad.
Square root both sides.
Isn't that what you just did on the other side? You just basically solve for x to find the domain.
Well, I was suggesting we would do x squared minus 16 is less than 0. And then that's x minus 4 times x plus 4 less than 0, which tells me I've got critical numbers at minus 4 and 4. And then I plug in points. I've got pluses over here, minuses in here, and pluses over here. And so my solution is like minus 4 to 4. So you're right. Why do you have to do it like that? Well, let's see here. Well, you take the I mean, you say take the square root of an inequality, right? Let me write it this way: x squared less than 16. So you're like, x is less than the square root of 16.
Yeah, so then you get plus or minus 4. Yeah, plus.
So x is less. You say x is plus, or you say put a plus or minus here.
Yeah, so technically that's the same thing, right?
Can x be both less than 4 and less than minus 4? I mean, so you're interpreting this to mean minus 4 less than x less than 4? Is that right?
Yeah. Isn't that the same thing as what you wrote on the other side?
That is what we found over here, but over here, this is careful. Over here, this can get you into trouble because what happens if we go the other way? Like suppose instead of having 16 minus x squared, I had f of x equal to log base 3 of x squared minus 16, right? So then you'd have like, okay, so you want x squared minus 16 to be greater than 0, right? So x squared is greater than 16. So I suspect you'd say take the square root of that. X is greater than plus or minus 4.
Which is the same thing with what you wrote on the other side.
But
I don't understand the difference.
what is this? What does this mean?
X plus, or x is great. 4 is greater than x. No, opposite. Minus 4. Yeah, negative 4 is greater than x. Plus 4. Yeah, 4. It's the opposite of what the other thing said.
And x is all right. So what am I supposed to write here now? Okay, so what does this mean? I mean, just tell me what that means is all I'm asking.
4
greater than,
x, yeah.
but the thing is, this here, we have x squared minus 16 greater than 0, right? So that's x minus 4 times x plus 4 greater than 0. So we draw our number chart, our number line. We put our critical numbers, which in this case are minus 4 and 4. 4 from this one, minus 4 from that one. And it's plus over here. It's minus where it dips down below right there. So the solution is actually x less than minus 4 or x greater than 4. And those aren't the same x. So like, I mean, this is why I try to use number line, because you can get, I'm not saying that there isn't something you can do with taking the square root of an inequality. Like, it's possible, but we have to be really careful there. You don't like completing the square that much. Well, here I'm just factoring, right?
Yeah, I mean, but like, having them probably gets more complex.
Well, you can still use the number line. You just have to figure out everywhere that the input is either undefined or 0.
Don't you have to use this, you have to find this, you have to find, complete the square to even find a critical number?
I guess in principle you have to complete the square to make sure that you can't factor it, or you could check the discriminant to show, so what I'm trying to say is I would encourage you not to, I would just say don't do it this way, please, because I don't think it's helpful. I really don't. Let me try to say this. The thing is, the square root of x squared, what is it? I think one of the fundamental problems there is, I don't think you're right. I think if a is less than b, right? If a is less than b, I do think that that implies that the square root of a is less than the square root of b. This is true, all right? The square root function is increasing. It's true. The trouble, I think, with your previous arguments is that the square root of x squared is not equal to x. The square root of x squared is equal to what? Like, is the square root of minus 5 squared equal to 5, minus 5?
So, minus 5. Or no, it's plus 5.
Right, it's 5. Really, it's the absolute value of minus 5.
Yeah.
So that's the thing, is you have to put in the absolute value, and you got to think through it. And if you're not going to do that, then taking the square root of the inequality is very dangerous. So like, okay, so x squared is less than 16, right? So that says that the square root of x squared is less than the square root of 16. Well, that says that the absolute value is less than 4. And it happens that absolute value of x less than 4 has solution minus 4 to 4. Fine. But when we have x squared greater than 16, we take the square root. That gives us absolute value of x is greater than 4. Absolute value of x greater than 4 has a solution that's comprised of two rays going to infinity, one way to minus infinity, the other way to plus infinity. Like the solution to this, on the number line, if you look at it, it's like everything beyond minus 4 and 4, because one way you could interpret the absolute value of x being greater than 4 is that the distance from the origin to x is larger than 4. So if you know that, and you want to think through that stuff, then yeah, you can take the square root. But these are issues that you have to be aware of if you're going to go down that path. So I shouldn't rule it out. It is a valid method of inquiry. But I think that the number line just frees you of all that analysis. It just allows you to put down the critical numbers and check points in each region to figure out what the answer is, Let me show you a much more complicated example. Well, not really that much more complicated, but it'll look more complicated. Suppose you had f of x is equal to log base 7 of x squared minus 9 over x squared plus 4x plus 5 times, x plus 2 times x plus 10. Find the domain.
Okay, so this, our critical numbers would be positive 3, negative 3. 2, no,
Yeah, yeah.
2 and 3, and 2, or negative 2, and
Mm-hmm.
negative
So you said plus minus 3, negative 2, negative 10, and what else?
10. Wait, plus or minus 3, minus 2, minus 10, and then minus, 2 and 3. Just 2 and 3 again.
Oh, no. See, that's where, so you said something about completing the square. My point was like this is where that would happen. So this is like x plus 2 squared plus 1 on that quadratic factor, at which point you see, oh, that can't be factored. So it doesn't give you any places where the denominator is 0. So it's like it's a non-player, So yeah, the critical numbers here are 3, minus 2, and minus 10. So you can't just say that's greater than 0 and take like a square root or something, right? But the number line technique still solves this inequality problem. And so we need that this, let me call this thing f of x. We need f of x. Oh, I better not call it f of x. That's already taken, right?
Yeah.
Let's call it g of x. We need g of x to be greater than 0, right? Because the log has to take a positive input. Now, is this question on the test Thursday?
Any of this isn't tested, right?
The question, is g of x greater than 0, could well be on the test.
Oh, yeah.
Not the logarithm part, but the part that's actually the majority of the analysis here could be there. That's why part of why I'm doing it right now, because I know you guys need review of how to solve inequalities, right? I mean, that is part of the test, and that's the page that got skipped. I mean, the one that's on the page that got skipped is easier than this, right? For sure, it's like way easier. But you could solve it with the same technique. So we've got, minus 10. Make sure you put them in order. If you put them out of order, this does not work. I speak from personal experience. Minus 10, minus 3, minus 2, and then 3 goes over here, right?
Yes.
And then we just need to plug in some points, basically.
Wait, so that's one of the things we're doing with this. We're just doing it.
Well, if I was asked this question on the test, the question on the test would just be like, problem solve, x squared minus 9 over x squared plus 4x plus 5 times x plus 2 times x plus 10 greater than 0. Like that's how the problem would appear on the test. There wouldn't be anything about logarithm because that's after test 3. But these are not disconnected discussions, I mean, like the things we learned for test 1 and test 2, we still use for test 3,
Yeah, we learned this.
It's math.
Too, right? This was test 2, right?
Yeah.
Basically, finding the map, right?
That's a good question. Did we have this already on test 2? It seems like so long ago, I've forgotten already. Oh, me. I'll tell you for sure here in just a second. Let's see here. So on test 2, we had like graphs of functions, average rate of change, linear functions and models, transformations of functions, combining functions, one-to-one functions and their inverses, and additional examples. So no, I don't think I really had it on test 2, not deeply anyway. Let me check. we had like evaluation of a function, domain and range of function, right? Difference quotient, average rate of change. But we did have domain questions which involved greater than or equal to 0. So you're not wrong about that.
Wait, isn't that what you're doing when you're solving for these?
Yes, but my point is the domain questions on like test 2, they were much, much simpler. Like it was, oh. So like, yeah, there are things like the square root of 6x plus 7 or something. Find the domain of that function, right? So the inequality we had to solve was just 6x plus 7 greater than or equal to 0. So we didn't really need the number line technique there, but we do here.
So we used to use the number line.
Yeah. Yeah, I think this is, so this is a potential question to test Thursday. Now, I probably won't ask one quite this complicated because I can figure out if you know what you're doing without getting so complicated as this anyway, you know, as you can see from the quiz. All right, so we need to plug in points to figure out the sign of things for this problem. So like, you know what I usually start? I usually start with like wherever 0 is because it's easy. Like 0 is here. So like what would g of 0 be? Mm-hmm. But use the original form, it's even easier, right? Right, -9. Yeah. 5 times 2 times 10. So it's less than 0, right? So we got minuses there. And look at the factors. Do any of them bounce? I mean, no, they're all linear factors, right? So that indicates sign changes at each of the critical numbers.
Wait, how do you know if they, oh, because
They're not squared. When the factor is squared, it can maintain the sign across the critical number. It like stays plus to plus or minus to minus.
wait, so if the entire thing is squared?
If the factor in question at that critical number, like the corresponding factor, so the factor corresponding to 3 is x minus 3, right? The factor corresponding to minus 3 is x plus 3. The factor corresponding to minus 10 would be like this x plus 10.
Okay, so like,
They're,
oh, that was the only one that had a square.
yeah, there's none of them with squares. The only one that has a square is this guy, but he's always positive.
Oh, I understand.
So, like I said, he's kind of not even a player in this game. He's just always positive. So if you're always positive, people don't care what you say. It's a life lesson here. Should be more negative. Sorry, I'll shut up. Okay, so greater than 0. I mean, apparently it's kind of complicated, right? But it's the domain of this f. Mm-hmm. Right. And so in this context, we don't include the endpoints because we cannot allow 0 to enter the logarithm, right? In contrast, in test 2, we're finding domains of square root functions as long as it's like square root, not division by square root, but actually multiplication. I mean, just square root, plain and simple, like this one, greater than or equal to 0 was the condition we put on the input to the square root function. But yeah. Okay, let me move on here. But I'm glad we had this discussion. I think it's very good discussion about this taking the square root of the absolute value. I mean, square root of the inequality there. Like, I know that's something that bothered me for a long time. Okay, so now I need to talk more about additional tricks, or you could say techniques. So here's something I use a lot. If I want to take like a to the power x, right? I can convert that to e to the x as follows. This is e to the natural log of a to the x. So this is just an identity. E to the natural log of a positive thing is the positive thing again. So this is just, you know. But then the power law gives me e to the x times the natural log of a. So this means I can rewrite exponentials in a certain base as exponentials base e with a multiplication in the number. So like, let me put this into practice. For example, if I wanted to think about y equals 2 to the x, I could just as well think about e to the x times the natural log of 2. Like I can convert 2 to the x to e to the x times log 2. It's a very sneaky trick. Let's see here. Let's see, another example. So sometimes you might find a formula like this. The number of particles at time t is equal to the initial number of particles times the exponential of e to the minus t over what's usually called tau. But that looks too much like t for here. So I'm going to use big T, t over t. So this is the formula you might find in what's called like radioactive decay. So in the other formula, I might have told you, might have not before, like e to the minus kt. So here k is the decay rate, right? And so k is related to big T is like, oh fine, I can't use big T here, guys. I'm sorry, it's bothering me. I'm gonna have to use little tau. Usually people use tau for this. Tau is usually called the time constant. Just, that's tau, it's a Greek letter. Maybe you guys know that. No? No Greeks? Okay. It's all alpha, betas, and gammas, no taus. Tau just doesn't have the same ring. Yeah, fair enough. So, we could look at this. I mean, here's a question. So if you want to rewrite this, n naught e to the minus kt is equal to 1/2 to some power, let's say p. Can you solve for p? And that's still not what I want. I want. Sorry, I'm trying to think if I want the n naught outside. I think I want the n naught out here. N naught times 1/2 to the p. That's what I want. So first of all, we could cancel the n sub zeros, right? Like just cancel those out. So we want. Yeah, how do we solve that? I want to solve for p. Solve for p, yeah. So I should, disclaimer guys, what I'm doing right now is pretty weird. So if you're not quite following me, it's okay. Like I'm doing something a little bit odd at the moment, yeah.
Can you like square p? Can you like, not square, but like maybe to the p power or something like that?
Oh, I know. Couldn't we do the same trick again? Like we could convert it to an exponential? Like, you could square it, but I don't think that would help us any. But I can do this. I can do that e to the natural log of 1/2 to the p, you know? Right? And that's equal to e to the p times the natural log of 1/2. And then I need to share with you guys a principle. Well, then at this point, you could take the natural log of the equation. So I've got this is equal to that, right? If I take the natural log of both sides, what do I get? Natural log of e to the minus kt, natural log of e to the p. I mean, I'm sorry, I'm doing things in kind of a not great way. I mean, really, once you have e to the something equals e to the something else, then by the one-to-one property of the exponential, you can say that the arguments are equal. I'm just kind of beating around the bush here. Let me take a step back here. There's an easier way to see it. Sorry, I sometimes get carried away with that identity. That's my bad. What I should have told you, which would have been easier, is why don't we just take the natural log of this equation? Because natural log will undo the exponential. So what happens, natural log of e to the minus kt, natural log of 1/2 to the p. Well, on the left-hand side, we just get minus kt, and over here, we get p times the natural log of 1/2. What is the natural log of 1/2? Well, that's minus the natural log of 2, right? Notice that natural log of 1/2 is natural log of 2 to the minus 1. So that's minus the natural log of 2. That's why I said minus the log of 2 here. So this is minus p natural log of 2. So what's my p equal to? P is actually equal to, yeah, p is actually equal to kt over the natural log of 2. There's a minus on both sides. you just say you're tired. I know the feeling. So let me circle back and put this all together. What we have then is n naught e to the minus kt, right, is equal to n naught 1/2 to the what power? To the kt log of 2, right? And I don't know how I got, I'd like to restate that in terms of the, good grief. All right, so that's equal to n sub 0 times, let me write it out here, 1 over 2 it's fine. 1/2 to the, I'm trying to think of a way to express this here. So that's really t divided by tau times the natural log of 2. So if the number, let me rewrite that again. N of t is the initial number of particles times 1/2 to the time over tau log 2. Here, tau is equal to 1 over the decay rate. Are we doing physics? Well, physics is, I mean, chemistry maybe. This is the Halflife formula. So what's the half-life? If you have radioactive particles, right? If you got a bunch of them sitting out on a table, and then through radioactive decay through the weak force, right? Things changing form through the weak force. Half of them change to something else. At that time, like statistically, the time that that takes is called the half-life, right? And this bit of algebra shows you the relation between the half-life and the decay rate. So like, what is that half-life then? What is T1/2? So n of T1/2 should be what? It's n sub 0 over 2, right? It's when you have half of the initial amount. And so we can figure out what time that is, right? That's So can we solve for t? So I'm trying to say here, solve this for t. Yeah.
So could you take the log? You could take the log of
So you're thinking take the log of both sides? Oh, I think we should cancel the n sub zeros, right? Because that's kind of beside the point.
So then we got 2 equals 1/2.
Well, yeah, 1/2 equals to 1/2 to the t over tau to log 2. Yeah. So you take the log of that? Okay, I'll allow it. So the natural log of 1/2 is equal to the natural log of 1/2 to the power t over tau log 2. So by properties of logs, that's t over tau log 2 times the natural log of 1/2 equals to the natural log of 1/2. So what happens with the log halves? Right, they cancel. And well, 1, right? T over tau times right. And my bad, I was supposed to be saying T1/2 everywhere. It's kind of obnoxious, but this is the half time, I'll put them back in. Right, yeah, so T1, the half-life is 1/2, T1/2 is tau times the natural log of 2, or in terms of the decay constant, it's the natural log of 2 divided by k. Now that we've gone through all this mess, I probably can show you an easier way to get to that formula. All right, so we're doing things somewhat inefficiently at the moment. I want to point out some things to you guys. So if we're going to solve a to the power p equals a to the power q, right?
Yeah.
Then this implies that the natural log of a to the p equals the natural log of a to the q, right? Which implies that p log a, right? And of course, if I just used log base a, of, took log base a of both sides, I'd immediately get p equals q anyway. I took the natural log just to make a point, because that's what we were doing over here. Yeah. But this, you notice what happened is the log a's cancel, and we just get p equals q. So like, this is a theorem, usually called the one-to-one property of, a to the x, is that a to the p equals a to the q implies if and only if p equal to q, actually. And like, we can derive that by taking the log, but like, if you see it, then you don't have to take the log. You can just say, oh, p equals q. In this context over here, what I'm trying to say is, once I had 1/2 to the 1 equals to 1/2 to the t over tau log 2,
Then you could have just said T equals
I could immediately gone to that blue equation. If I,
take the log out.
right. But taking the log is not bad, because taking the log, that way of thinking, allows you to solve other examples. Like if you wanted to solve 2 to the x equals 3 to the, say 2x minus 1.
But by that, all you would have to do is say x equals 2x minus 1.
But we can't do that now because it's not, the bases don't match.
Oh, okay.
See, this is only good when we have a and on both sides.
So then you get to take the log over that.
Now we got to take the log, and the log does something. It tells us what scale factors are needed to match up the powers, basically. See, this is, x log 2 equals to 2x minus 1 log 3. And that we can solve. Isolate x.
Put log on the other side. Log 2. Right? About log
2 log 3 times x is equal to minus log 3, right? So I move the minus 2x to the other side, and then factor the x out. So apparently x is equal to, the log of 3 divided by the log of 2 minus 2 times the log of 3. And I forgot my minus there. So my larger point in this discussion was like if you're in a chemistry class or a physics class, you might not use the e to the something. You might use 1/2 to the something, because then that ties into the half-life, right? But you can relate the 1/2 formula to the e formula through the math we're looking at. I think it can be done more clearly than I did it today. My apologies. It's a little bit muddy what we did. I probably should have waited to do that example until we had done much more of this sort of thing. My apologies. Now, there is another thing we should talk about, which is the so-called change of base formula. So suppose you wanted to calculate log base 7 of 17. If anybody have your calculator out? Can you find log base 7 on there? I'll tell you this, I wouldn't know where to find log base 7 on my calculator. Oh, you have log base 7 on your calculator? Curses. You have a log base A? I mean, you might. What'd you get? Tell me the number. 14.36. 14.36.
Yeah, but 6 is running out already.
Huh.
It's probably not right.
That doesn't feel right to me. But let me just. So my the point I'm trying to make, and I may be failing to make it, is that a lot of calculators don't have a like a log base. Either they don't have it or it's not convenient to calculate like log base 7 of 17. There's usually a natural log built into the calculator and log base 10, maybe log base 2 sometimes. Okay, well, 1.456, roughly speaking. I'm using Wolfram Alpha at the moment. All right, but there's another way you could do this by what's called the change of base formula. So log base whatever, log base b of x is equal to log base a of x divided by log base a of b. So, or if you like, the natural log of x divided by the natural log of b is a special version of that. So like, if I want to calculate log base 17, excuse me, base 7 of 17, I can just take the natural log of 17 and divide it by the natural log of 7. Every calculator, every scientific calculator will have natural log. It should be like an easily accessible, right in front of your button, you know. So like natural log of 17 is 2.833, roughly speaking. Natural log of 7.
Natural log is 9.45, or for the entire thing.
1.946. Sorry, not to interrupt you, but if I don't say it, I'll forget it. And then if you divide those two numbers, we should get about 1.456. So this is the change of base formula. If you want to convert from one log to another, you can do this. All right. So now, anyway, I know you guys got to go vote, so I'll let you out early today. How's that sound? What? Oh, I will say this. There's only one thing I have to say about Election Day, and I say this often whenever it comes up. Like, why is Tax Day the other side of the year? Like, Tax Day should be the day before Election Day. So people have on their mind, this is what's happened, you know? And that way, you have more accountability.